we'll move over to the cool part, which is talking today about Venice. So just a quick intro about me that I'm sure most of you do not know. My name is Zach. I'm a senior staff engineer here at LinkedIn. My career background over the last 12 years has been in distributed databases, kind of a short list of ones I've worked on. And I joined the Venice team at LinkedIn back in 2019 and have been working on Venice ever since. I'm excited to have you all here for what is our first Venice Ska and to talk to you today about this platform. So what the heck is Venice? Venice is a database that specializes in hosting derived data. What is derived data? Well, we define derived data to mean data which has been derived from a primary source. This means it's maybe been formatted, inferred, maybe tossed around a little from other data sources. There's a previous talk that was given by Felix at QCon London that you can take a look at if you want to learn more. It's the title's at the bottom here. It's what is derived data, and there he looks at what derived is and what patterns surround it. So why host derived data in Venice? Well, as Manu alluded to, or I didn't allude to, he just outright said, the goal of Venice is to be the default storage. If you want to learn more about derived data and patterns that surround it, check out that talk. It's the name of it is at the bottom there. It's what is derived data. So why do we host derived data in Venice? The goal of Venice is to be the default storage solution for online AI use cases. In order to facilitate that, we try to offer a feature set which enables these users to be successful with featured data. A category of data that falls under the umbrella of derived. One thing that we have observed about featured data is that it needs to frequently change, and I'm not exclusively talking about row-by-row updates, which you might be used to seeing in many other databases, but often entire data set refreshes. To that end, Venice supports high-throughput data ingestion through batch sources, streaming sources, or both. And we'll take a look at that later in the presentation. We'll walk through kind of how that works. Another facet about feature data is, well, it often needs to be very low latency, or retrieved at very low latency. Just as a working example, imagine that you want to score 5,000 entities, and for each entity, you need 100 features. The result of that is you're going to need to pull 500,000 features. And on top of that, you'd probably like to spend most of your latency budget on that request running the model and not querying it out of the database. Clients want a latency that's something on the order of milliseconds, so low latency and performance is a critical feature of Venice. And we'll go through kind of what that looks like as well. And finally, we want users to be able to focus on business needs. We get out of the way as much as we can. Venice is designed to be as self-service as possible for its partners, so that the infra is there when you need it and doesn't require significant effort from partners when they want to use it. Okay, we open sourced Venice back in 2022 and have been developing at full steam ever since at LinkedIn. One of the talks today is we're going to go through what we've worked on the last year. And we've gotten, most of our contributions come in-house. We've also gotten some from the community. You can see our talk at Strange Loop, where we open source Venice in front of a live studio audience. And you can check it out there. That's at the, again, it's at the bottom there, open sourcing Venice at Strange Loop. Okay, so I'm going to split this part of the talk between the read path and write path of Venice, starting with the write path. How does it work when you want to, dump data into Venice? Well, getting data from some source, be it a data warehouse kind of source or a streaming source, to something that can be queried in the online is, one of the main use cases for AI users. I'm going to walk through the write path for something called a hybrid store in Venice, as it happens to cover the majority of the features in this category. Users of Venice have data in offline storage or streaming storage or both. Hybrid covers the basis for both of these types of sources and goes through a 4-step process for ingesting that data that users don't need to fret too much about, as it's orchestrated by the platform. Our initial state or steady state looks like this. We've got a stream processor, and it's writing data to a Kafka topic that acts as a real-time buffer. This topic is owned by Venice, and the user doesn't have to provision it or even know about it. Venice takes care of it. Venice ingests the data out of that buffer and applies it to a current version. And a note about that, a note about versions. Venice is a versioned database. Batch pushes may optionally create new versions, and data can be applied from nearline sources on top of that. Within Venice, we have the notion of a current version, and this is the version from which we serve read traffic. So now this slide shows what happens when a push begins, a new push from some offline data source. This is something that can run daily or on some schedule as defined by the user. This creates a future version. A future version is loaded in parallel, separate from the current version. This allows us to ingest it at high speed as we don't have to worry about locking rows from normal read traffic. And it means that the user gets a consistent view of the data set because we will not serve reads off of this future version just yet. We won't ever serve traffic off from a partially ingested version or serve traffic from multiple versions. And this is to give the user a consistent view of their data set. Next, once the version push is done, we replay data out of the real-time buffer. The reason why we do this is because often data sets from a warehouse or data lake environment might be stale. This kind of scenario isn't hard to imagine, especially when you consider that an input data set might be output from some feature compute pipeline. It can take a while to vectorize a large input depending on its size and its complexity. Users are able to specify with their push or statically on the store from where in the real-time buffer they would like data to be played from once the push completes. Once the real-time buffer has finished replaying, V2 is now caught up and can become the new current version. When the version is marked as current, as you can see, we shift read traffic over from it, and V1 is now our backup version, and we'll retain it for some time. So long as Venice retains a version, we'll keep that version up to date with new data from the real-time buffer. The reason why we do this is to prevent the backup version from going stale and enabling our clients to have the option to be able to roll back a version should they need to. You can imagine this happening if maybe you pushed a new feature set and suddenly noticed your business metrics were dipping. Now, within Venice, you have a handy escape route from that unfortunate result. So now some numbers, so you know we're not messing around. When we open source Venice, this is what our usage numbers looked like. We were sitting at about 1,400 pushes a day, about 1.2 petabytes written per day, and 3.3 trillion rows or features, or many features per row, depending on how you look at it. And since open sourcing, we've had a 21% increase in the push jobs, a 71% increase in data written per day, 2.1 petabytes in March, and I think now we're a bit closer to 2.5. These numbers are now a few months out of date. Not too bad growth, I would say. And we've gotten some capacity requests in the last 2 months that I think should steepen this trend even more as our industry collectively obsesses over AI adoption. All right, so we talked about writing data to Venice, but Venice isn't just some bit bucket. You can read data out of it too. So let's talk about the read path of Venice. We offer a few libraries when it comes to reading data out of Venice. The first one I'll talk about here is the first library that we shipped when Venice went to production in 2016. This is the Venice Thin Client. The Venice Thin Client is a stateless client that connects to the routing layer of Venice, which is also stateless, to discover which cluster and shard has the data being requested. This is a two-network hop architecture where a request transit from a client application to a router, to a stateful server, and then back again. Despite this two-hop setup, we give what we think are decent latency numbers. Within LinkedIn, we promise our partners a single-digit millisecond latency for single key gets at the P99. Now, in order to push the envelope a bit, we have a new client called the Fast Client. The Fast Client essentially contains the Venice router code as a library instead of a service that enables us to skip the routing tier. This is a relatively new client, and we've mostly only worked with some power users to utilize it just to make sure we remain in a state where we can make and publish changes quickly to a smaller audience of proactive adopters. They're also proactive developers, but mostly we're concerned about the adopter part. We are transitioning quickly to declaring this library stable enough for all users to be able to adopt, though it is there in open source, so you can use it. And we've been running it for over a year now in production with different use cases. With the Fast Client, we are able to promise a P99 latency that's less than 2 milliseconds, though it really ends up being even less than that, often below a millisecond. We just give us a little extra padding to keep expectations in line with what we know we can absolutely provide to the site. And finally, we have the Da Vinci client. Following with our trend of eliminating network hops from the read path, the Da Vinci client works by eagerly loading the dataset to the application, enabling zero network hops. Data is loaded from the underlying Kafka topic into a local RocksDB, which can be configured to store data on SSD or in memory. We found that on SSD, we tend to see about 200 microseconds latency, and for RAM, single-digit microsecond speeds. A major partner within LinkedIn that uses Da Vinci is Search, is our search infrastructure here, which needs to be able to query data at very low latency in order to rank results in a timely manner. All three of these clients have the same interface and make available nearly all of the same APIs. Single gets, batch gets, and a feature we called recompute. Recompute is a feature that allows for doing vector math in the database. Things like dot product, cosine similarity, and Hadamard product. These are operations which are popular amongst AI developers. And we have a blog post titled Supporting Large Fan-Out Use Cases at Scale in Venice. And that's in the LinkedIn engineering blog. You can go check that out and see how we're using that to kind of improve what we can get out of the hardware by shipping less on the network by just doing these operations locally. And then, yeah, so there's that blog post. We make all these libraries available under the same interface in order to, which is my next topic, let users defer decisions. We try to make sure that we don't force users to decide on one client or solution for read or write path upfront. Users are able to pick some initial choices, and then down the road, experiment and decide if some of the other offerings work better for the use case with a simple library swap. And this is, with the intention here is to not, basically trip us up with future costly migrations if the user, gets to some point and suddenly they're backed into a corner. This is something that we try to do to make the catalog open to our partners. So we're going to mirror what we did for the write path here. We're going to look at how we scale for the read path. Again, back in 2022, when we first open sourced, we were looking at about 99 million key row lookups per second. Any bets on how we've done since then? Hands up for 10%? 20%? More? Okay, so optimistic bunch, and you rightly so. Spanning about a year and a half, we've grown by nearly 70% in this path. Largest increases coming from batch gets and read compute requests. And each key can be understood to mean that it's a query for one or many features. It's also worth noting that this just includes the data that hits our servers. I know these numbers do not include access from Da Vinci applications, I don't believe, which means that, and that's just because, for collecting that data, because those use cases are running at such high throughput, actually collecting those metrics is pretty costly. So this is a conservative estimate over, how things have increased over this time. So let's sum things up by looking a bit more at our scale numbers and our growth, along a few other dimensions. So this is the table that I showed earlier, and I'm going to layer this with one other piece of information, and that is with the number of data sets that we've added to Venice since then. This is meant to be representative of how the metadata load has grown within the platform. So for every store, we have some amount of overhead in terms of what we need to track about it and how to load balance it through the clusters. So this isn't necessarily stressing the hot path, but it does stress the control plane of Venice, and we've been handling it fairly well despite pretty good growth. And then one of the cooler things is that despite all this growth, despite seeing nearly a 70% increase in data read and over 70% increase in data written, the amount of hardware that we need to facilitate that growth has only grown by 10%. Of course, for good infra, we need to be able to grow our clusters and scale horizontally, but we've managed to, over time, make improvements within Venice or with partners to allow for us to be able to squeeze more out of the hardware that we have. As infra developers, we don't often get to stick our flag in a feature which drove product revenue. Our version of that is not in money that we make, but in money that we save. By by serving more with less, or preventing us from having to buy more hardware. This is how we as internet developers make money, usually for the company. Um, Also, more hardware tends to add some amount of inertia when it comes to the likelihood of things going wrong and for performing things like normal upgrades, normal maintenance, right? The more servers that we have, the more these things are going to naturally kind of slow us down a bit. So being able to grow this much without a proportional hardware need is a major accomplishment for the Venice team, both in cost and for operational means. If you want to learn more about Venice, you can check us out at venicedb.org. We every other Wednesday have a meetup for potential adopters and contributors that you can find out more about on venicedb.org and in our open Slack. We're having one tomorrow morning, so if folks are interested, dial in, come talk to us. And you can also check out the code on GitHub. I try to curate a bug list for first-time contributors there. If you want to get your hands dirty, go check it out. We are always looking for new contributors. Now, for this last part of the talk, I'm going to go over a few lessons that we learned while implementing Venice and rolling it out over this time, such as discussing the challenges we hit along the way and how we solve them, and what advice we can give to you all, system maintainers, I assume. Start things off. One important thing for any system is to understand the bounds of the workloads that you need to support, and to realize there may not be one answer to the kind of bound you need to be cognizant of, you need to be aware of. In Venice, each data set is assigned to a cluster, and most Venice clusters at LinkedIn end up being storage bound. In storage bound cases, we are limited by how many SSDs we can pack into that cluster. AI datasets are getting bigger and bigger, and the number of input features seems to only grow with time. It seems like every quarter they want more and more. So this is pretty typical. However, there are some use cases which are what we call traffic bound, and ending with in that sense, with a very different set of requirements. I'm going to define traffic bound to essentially mean that just the amount of read throughput to this cluster is going to be where we have to expand. And we end up embracing this dichotomy. We tune our clusters differently to support these kind of two paths for the kind of bounds we hit. To give an example of the kind of things we do, for a storage bound cluster, normally we keep a replication factor of 3 for the sake of online redundancy only. This allows us to lose a replica and upgrade concurrently without fear of losing availability completely. And additionally, we store all the data on disk, just to kind of pack that in. Those are all your format. However, in cases where we're traffic bound, we're going to go a pretty different direction. The replication factor isn't just about redundancy in this case. It's about scaling the read throughput across a comparatively smaller data set. To facilitate this, we put the data in RAM and set a higher replication factor in these clusters. Typically 4 or 6 replicas, though we have vetted Venice to go as far as 12 replicas in a slice. Slice meaning replication. We have these two types. Now comes what goes where, right? How do you do this, right? Well, which store goes on which cluster is decided by operators today. We don't typically allow the user to select which cluster they go to. And client applications themselves have no notion of it. There's no config out there in Venice where a user can wire to a specific cluster that says, give me the store in that cluster. No, they just know the store, they talk to our discovery service, and we route them. Operators are able to bin pack the stores to appropriate clusters without the partners noticing. So we are able to use our store move. We have a store move feature that allows us to take certain stores that we observe to fit in one of these kind of patterns. Maybe if it's like a storage bound one that's really aggressive and it's relatively small, we'll move it, or maybe even vice versa to make more room in somewhere else if maybe we made a bad call at some point. This allows us to be proactive when we observe these things happening. We don't have to go talk to a partner. We don't have to orchestrate a migration, do a deployment, that sort of thing. We can just do it, and it just works. And this segs us into the idea that don't let users do the operator's job. One job. Okay. Interesting levers are owned by the operating team, so we can pull them when we have to. Our goal here is invisible infra, and if users are spending a lot of time, playing amateur hour on loosely understood configurations, that's probably not time or expertise well spent. So we try to reserve these things for our operators to, take the load off, to so to speak, both on the clusters and on the partners. Now, coming back to the storage side of things, since we're storage bound, we've looked at compression quite a bit. Not all data sets compress, unfortunately. Previously, we had some very careful schema design principles like don't store enums as a string or don't repeat namespaces for urns if they're always the same. But we found that this is hard to enforce and users don't really care to self-police much. So to try and ease things, we have used compression, and historically we have used gzip. Gzip, however, has some shortcomings. One situation we found was that in gzip, the payload is self-contained. So you might have some symbol like foo, and maybe it compresses well, but if it exists in a lot of records, then you just keep getting it repeated. Gzip works well when compressing across a large data set, so you can kind of build that symbol table across everything. But since we need to serve record by record, we have to compress record by record. So we can't really take advantage of those properties. Since then, we've been using a library called ZStandard. ZStandard is an open source solution that we came across that's worked really well with for Venice. It has a mode where you can train a dictionary outside of the payload and use that to decompress individual records. This ends up working quite well for Venice because we're able to compute the dictionary as part of the Venice push job and transmit it as part of that push to Venice servers, which need to decompress. ZStandard ends up compressing things very well. The most extreme case we found was a case where it was able to decompress store by 255x. This is a huge outlier. Don't go home and expect this, but it was pretty cool when it happened. It doesn't usually hit that, but it's at least we've yet to find a case where gzip compresses better than ZStandard. Usually ZStandard ends up compressing much better than gzip. I don't know, Felix, do you remember? Again, those urns. All right. So next to that, so coming off that kind of story about compression, another tenet we try to hold dear is tune things behind the scenes, right? So this is kind of in the same vein as don't let the users do the operator's job, but maybe slightly more specific. Taking the compression story as an example, enabling compression would net us an improvement in on-disk storage, but it might cost some amount of latency. And we don't want to be in a position where we, are, purely letting it go to the user. We are able to enable compression without the user, having to be involved. We can watch and observe, if there's a big negative impact, and we can revert easily should things, go a bit pear-shaped. Another type of data which is not very compressible are embeddings. Embeddings, for folks who don't know, are essentially an AI data structure that, to those of us who work in storage, just look like a big n-dimensional array of floating point numbers. You can do some compression on embeddings by rounding, but this costs you precision. In Venice, on a lot of stuff at LinkedIn, we encode things in Avro format. And Avro off the shelf isn't terribly performant with these floats. So we use an open source library that we contribute to called FastAvro. In FastAvro, we've had a lot of enhancements to make floating compression much more efficient and faster, specifically by utilizing some features in Java 9, like var handles. This has really improved the embedding heavy use cases, and you can check that out at the link on the slide. There's a lot of neat stuff in there. It's used very heavily at LinkedIn. Oop. That didn't go to the next slide. That's weird. Okay. Next, performance is the best feature. In this talk alone, we've spent a lot of time boasting about latency and improvements in throughput. And having good performance is what keeps the partners engaged and happy. Typically, partners who have come to depend on fast performance are really loath to part with it. So they're often coming back to us as their needs grow. We have another QCon talk here that you can take a look at, where two of my colleagues gave a talk on how we were able to get the Venice server to 1 million ops per second per node, which was a big milestone for us. You can check it out. It's by that same name. It's another QCon talk, and see what tips and tricks we leverage to get to that. Next tip, software versioning is also an important operability touch point for us. Mo versions, as it turns out, is not Mo beta. And having many different versions being active across clients and server versions increases the matrix of complexity of features and bug fixes. So we aggressively deprecate. Within LinkedIn, we have the tooling for making builds fail if they're on deprecated versions. And we have tooling to cut pull requests for version bumps across dependers to make sure things do move through the stack. And we try to do that fairly often. Our push job is kind of in tune with this, but it's maybe a bit more neat. Our push job runs within the Azkaban scheduler, and we use the Azkaban plugin system to deploy it. Users can't specify versions on that plugin, and that works as a symlink that we can centrally control. So we're able to be hands-on with how we ramp new versions of the push job to our users in a very centralized manner, which in turn allows us to be agile despite handling more than over 1,000 pushes a day. And then the last lesson that we'll share today, and this relates to the previous slide, but being able to move fast on versions only works if you keep things compatible. If you break your API a lot, looking at you, Avro, then you're not going to be able to push your upgrades. Think carefully about your APIs before they're out there. Once they're out there, you're on the hook. So be careful. Maintaining a forward and backward compatibility and releasing interfaces that know will kind of stand the test is an important tenet of our team. And that's everything I got. Thanks everybody, and I hope you enjoy the rest of the talks today.